Hi, everybody. Let's go ahead and get started. I'm going to be talking about on-target iteration in Unreal Engine 5.5 and beyond. In terms of an introduction, my name is Zosar Shaker. I'm a lead programmer on the Unreal Engine Foundation team. And I want to be clear as I'm presenting this material that this is not just like, hey, look at my work. Rather, this is the result of a lot of development effort by a lot of talented developers on the Unreal Engine team, spanning Foundation as well as consoles and other teams. I'm going to be going through a lot of material, so we're going to cover a lot of ground. If it feels like things are going fast, just know that in the end I will leave time for questions. And also I've got a link near the end of the presentation that will direct you to documentation, so you can find out more afterwards. So what we set out to do was improve content iteration speed on consoles and mobile. What we want is for content iteration on target platform to be closer in speed to what code iteration is like. I'm an engineer. When I need to make a change and see it on target platform, I have to go through a recompile process, and that takes time, but it's much less time than what a content creator has to go through when they want to see content changes on target platform. So we want to close the gap there. So what's involved in the current pipeline for content iteration? I'm going to focus on three specific phases: cook, stage, and deploy. There's other phases we could talk about: first-party packaging, boot and load time. Those exist. I'm not saying those don't matter. Just it's these three specific phases that I'm going to focus on. And they happen in that sequence: cook first, then stage, then deploy. So what's involved in each? Well, cook is the sometimes time-consuming process to load and save all the data in the game for a specific platform and store it as thousands of files in the saved cooked platform directory. From there, we do a stage, which copies the game executables, as well as those cooked output files that were produced from the first phase, and either store them as they were, thousands of files, only now copied over into the staged builds directory, or we can stage to container files. That's pack files or UCAS files that are aggregating that cooked data into fewer files. Aggregating and sometimes compressing that cooked data into fewer files. But those also exist in the staged builds directory. And then finally, deploy. It's relatively straightforward. It's just the act of taking the staged build and copying it over to our target platform, whether it's console or mobile device. And once it's there, it's ready for execution. So I'm going to be showing some diagrams with example data on them. I just want to note the data that I show is hypothetical. It's just meant to be representative of a current gen console game in terms of size and quantity. Every data set is different, but this is just an example. So one way to visualize this is as shown here. Starting with the cook phase, that is taking in UAsset files. It is also taking in files from the DDC or derived data cache. And then it is writing out cooked output files under the saved cooked platform directory. So in this example, hypothetically, let's say that produces 60 gigabytes of output spread across 1 million files. From there, we've got the stage phase, and the stage phase takes in the game executables, which are comparatively smaller and fewer, let's say 5 gigabytes in 4 files. And it takes in all of the cooked output files produced from the first stage, cook. So it has to read all of that back in, and then it has to write out the staged game. In this example, I'm staging to container files, which means I'm producing pack files, UTOCs and UCASs. And so you can see the relative proportion of the input and the output. So in this case, the output is 65 gigabytes of data spread across 80 files. We've taken those million files and aggregated them into much larger container or pack files. And then finally, deploy. Deploy, like I said, relatively straightforward. Taking the staged build, getting it over to the target device. So it's got to go from our workstation to a target platform, and that happens over either a network connection or a USB link in the case of mobile devices. So putting these together side by side, you can visualize it like this. So you can see cook, stage, deploy, and all the same as what we saw earlier, just strung together. So you can see how the output of cook is also fed in as the input of stage and onwards until we end up with a build on our target platform that's ready for execution. Okay, so what are the problems that can come up with this? Well, there's no shortage, especially as games get large. The cook can take 60 minutes or more. It has to load and save every file in the project. It repeats processing of files that haven't changed every time you cook. It's sensitive to DDC latency and hit rate, and it writes out thousands to millions of files. And also, it doesn't use multiple cores very efficiently. Stage can take 5 to 90 minutes depending on compression. If you're doing a high level of compression, it's going to take longer. If you're doing no compression or a low level compression, it's going to be shorter. A lot of data getting copied around on disk during stage, and much of the work is actually irrelevant to a person iterating. It's not strictly necessary. And then when it comes to deploy, that can take 3 minutes or more. It tries to be smart by incrementally copying, that is copying only things that have changed. However, because we aggregate into container files, that somewhat undermines the incremental copy attempt that it does. So what we see is an outcome where content creators say, you want me to wait how long to see my work on target? And then they retreat to the relative comfort of Play in Editor or Pi. These problems aren't exclusive to content creators. These affect automated builds too, so there's more breadth to it than just the content creator workflow. So I'm going to start talking about steps we've taken that try and address or mitigate these issues. I'm going to start with stuff that's available in 5.4, then move on to stuff that's in 5.5, and then finally talk about future items in 5.6 and beyond. The first that I'm going to talk about is multiprocess cook. This has been production ready since UE 5.4, and for us within Epic, we saw a greater than 50% time reduction by applying it on Fortnite to our cook times on the build farm. We went from a single process cook to 4-process cook, and that reduced the cook time by over 50%. Critically, it has been reliable enough that Fortnite has been shipping with multi-process cook. The builds that it produces and ships to users have been produced with multi-process cook for the past 1.5 years. And our automated processes now use anywhere from 4 to 10 processes during cook, depending on how much RAM is available. It is critical to be aware that using multi-process cook is a trade. You're trading memory for wall time reduction, and you need to make sure you've got enough memory to make that trade. So besides having memory, it's also critical that you allow page files on your machines to grow and span drives. One of the common problems we've seen is that page files are constrained to only be on the system drive, which may not be large, and so allowing it to span drives makes it feasible to use multiprocess cook. The other thing to be aware of is that by using more memory, we have more garbage collects that kick in response to low memory situations. This can surface latent issues that already exist in your build. If you have dangling pointers after garbage collect, you might have had few or no issues before, but because garbage collection is happening more frequently, those issues can surface when you start using multiprocess cook. But other than that, we've not seen other issues introduced by multiprocess cook, not determinism issues or anything of that nature. In terms of how to make use of multiprocess cook, we've tried to make it relatively straightforward. For your project, you can go into your default editor.ini in the cook settings section and set a cook process count that indicates how many processes you want the cook to use by default. You can also set another value that's your cook process from editor in case you want to use fewer processes to leave some memory space for the editor. And regardless of what you've set up in your config, any invocation of the cooker, you can always pass a command line argument, cook process count equals n, and that specifies how many processes you want the cooker to use. And then it takes care of everything from there, launching other cook processes and the inter-process communication that happens between them. Okay, so that was multi-process cook. I'm going to talk about Unreal ZenServer next. This is something that first started to show up for people in UE 5.4. I mean, it existed before, but it became a part of the default workflow in 5.4. You're going to hear me refer to it as ZenServer or Zen. It's the same thing, just shortened nomenclature. And what we're doing with it is we're using it to store data when the file system isn't scaling to our needs. It's tailored for content pipeline use cases, and the way the engine interacts with it is via network sockets. I'm going to talk about how it's applied in different roles. So you'll hear me say Zen as X, Zen as Y, as I go through this presentation. So just some foundational information about how it works. First thing you need to know is it's a separate process. So when you launch Unreal Editor or other UE tools, they will launch ZenServer on your machine as a separate process alongside them when they're using a feature that requires ZenServer. It is available for Windows, Mac, and Linux. So you'll find pre-built executables sitting in the engine binaries directory. And the ZenServer process services requests and provides responses over a network socket. We're using HTTP today, but that's an internal implementation detail that shouldn't be relied on. We're considering alternative protocols. So what does it look like? This is a bit of a hard question to answer because it doesn't look like anything. In this example, we've got the editor running, and you don't see ZenServer. It's an invisible background process that you wouldn't be aware of if you didn't go looking for it. However, you can open up something like Task Manager or Process Explorer and observe that, yep, ZenServer.exe is in fact running. If you want to inspect its status, there is a standalone tool separate from ZenServer called Unreal Zen Dashboard that can be accessed through the editor by clicking the Derive Data button at the bottom, then launch Zen Dashboard. And its sole purpose is just to check on the status of ZenServer and provide information and stats about it. In terms of where it's running and where it's storing data, there's a lot of details to this that's important to understand. Namely, we deliberately install ZenServer to a folder under the user's app data directory. The reason we do this is that we want to ensure that you can sync your workspace even if ZenServer is running. So for that reason, we don't run it directly in place. We copy it to an installation directory and run it out of there. The other reason we do that is because by design, we're meant to have a single ZenServer instance running no matter how many installs of the engine or editor we have on the machine, even if they're different versions of the engine or editor. The intent is that the newest version of ZenServer is what gets installed and run, and it is capable of servicing all instances of the engine and editor of that version or any older version. So it's by design backwards compatible. That's where the process is installed and run from. Besides that, there's a question of where it stores its data. And by default, it also stores its data in a folder underneath the user's app data directory, a separate folder from the place where the executable resides. However, if you have set up a global local DDC path, this was a pre-existing setting in the editor, ZenServer will be launched to respect that path and store its data within that path. We highly recommend that large projects set this setting. So what should you use for the data location for ZenServer? The global local DDC path should point towards a fast local drive, not a network drive, and not a cloud or virtual drive like Google Drive. Okay, so now we start talking about the roles in which we're using ZenServer. The thing to be aware of is it's enabled by default in UE 5.4. It replaces the file system DDC layer on local disk. And this was an important step for us in having it in use on people's machines today before we use it for other things. And what it's given us is it allows us to avoid file system overhead as DDC file quantity gets high. In addition, it also alleviates a workload that the editor would have to worry about, which is how we do cleanup or garbage collection in local DDC. That now becomes a responsibility internal to ZenServer. And another benefit we get is deduplication out of the box. Internally, ZenServer is storing data in content addressable storage, which means we get the benefits of deduplication automatically. Okay, so that was Zen as local DDC. Now I'm going to talk about Zen as shared DDC. This is something that's becoming production ready in UE 5.5. This is a situation in which ZenServer can replace a file share DDC on a LAN or local network. This requires manual setup if people want to make use of it. It's not automatic, the way the switch over to Zen as local DDC was automatic. And there's how-to instructions that are posted as a knowledge base article, which will be linked to later on in this presentation. Zen as shared DDC has been tested under heavy use within Epic. We've replaced one-for-one all file share DDCs with Zen shared DDCs. And that's for all of our studio locations around the world, as well as our build farm. And it's been an improvement in terms of reliability and performance over the file share DDC. It's production ready on Windows Server as a host, but I just want to be extra clear here. It's ready for Windows Server hosts, but that means Windows clients, as well as Linux clients and Mac clients can connect to it. It's just the machine that's hosting ZenServer should be a Windows server. We are in the process of doing work to make it possible to host on Linux. It's not that it's not possible today, it's that we need to do the work of ensuring it's as performant and as reliable as it is on Windows Server. So one of the benefits we get from this right now is that historically, Macs attempting to use a file share DDC had to rely on the CIFS or SMB protocol implementation within Mac, and that wasn't always the most reliable thing. Now they're on an equal footing with any other client because we're using our own implementation for the client code. Okay, all right. We've covered a few things. They've addressed some aspects of our list of problems, specifically the sensitivity to DDC latency and hit rate, and the fact that we aren't using multiple cores very efficiently. All right, that's a couple things, but a lot of problems remain. So far, the things I've talked about have been pretty transparent one-for-one swaps. The stuff coming up is more disruptive. So let's have a closer look at cooked output. We are writing 1 million plus cooked output files, and this stresses the file system. What we found is on Windows, simply deleting the cooked output folder could measure as long as 20 minutes in duration when the file quantity is this high. And when we look internally at what's going on, the NTFS transaction log is filling quickly with many writes and deletes. And when full, it triggers a flush of this transaction log, and that blocks all reads and writes to that volume until the flush is complete. So one thing that we had considered is, well, okay, things like deleting the cooked output directory, we can do that asynchronously. Well, you can do that asynchronously, but when that flush happens, any read or write that is happening from any other thread is also blocked until the flush is complete. Okay, so this is a bit of a tangent, but I think it's worth people knowing about. Windows enabled last access time tracking by default in a non-server installs Windows in a Windows 10 patch in 2020. This had a number of consequences that people may not be aware of related to file system performance. The end result is that it can be punishing to editor startup and load times and asset registry scans. So, and this is very difficult to profile because of the way last access time tracking works on Windows, where it only updates if the last access time was greater than 1 hour. So run to run, it can behave very differently. So my suggestion is please consider disabling last access time tracking on your workstations. If you don't want to do it domain-wide, there is a engine plugin named Editor Sysconfig Assistant that can be enabled for your project, and it'll show up in Editor and say, hey, this system configuration setting is affecting performance for your project, and offer to change it for you. Okay, back to the topic at hand, cooked output. So fundamentally what we're seeing is that we're scaling past the use case for the file system, and the file system semantics around read and write transaction flushes, they're not what we actually need. So this is where we introduce Zen as cooked output store. So what we're doing here is we're writing cooked output to ZenServer. That means the cooked output no longer shows up as files in the saved cooked platform directory. Instead, it gets stored in ZenServer. There are a handful of cooked output files that we still end up writing to the file system. Metadata, INIs, and a few additional files specified at cook time. They get written to the file system and then externally referenced by ZenServer. So ZenServer is aware of them, but it's not storing them internally. Everything else is stored in ZenServer. Besides being able to write to ZenStore, for our pipeline to function, we also need to be able to read back from ZenStore so that staging, for example, can get the cooked output and do its job. So when staging to container files, the Unreal tooling can obtain cooked output from ZenServer or loose files on the file system and stage to a few container files, pack, utalk, or ucas. We just skip the intermediate state of having 1 million plus cooked output files. So the thing to be aware of is that it is off by default. Even in 5.5, it's off by default. You have to opt into using it through project settings, where you can enable the use ZenServer's cooked output store. That's how it's labeled in 5.5. One thing to be aware of is you must also use IO store for this to be effective. This is just to limit our configuration matrix. IO store is enabled by default. That only matters to you if you've gone out of your way to disable it for some reason. So what impact does this have? So first things first, if you have third-party tooling that relies on the presence of cooked output files, then that may require a change. So that's something you need to be aware of. Besides that, in terms of debuggability, some people expect to be able to like spelunk through cooked output files and as part of their debugging, and that's not possible when the data is stored in ZenServer. So we're currently investigating options for exposing access to the cooked output without compromising an efficient pipeline by default. Our goal is to have Zen as cooked output store enabled by default in UE 5.6. The debug features that we have in mind is to expose a web UI that allows you to navigate the contents of ZenServer, seeing which projects are stored within it, and then going into those projects, seeing which individual cooked outputs, like a Windows cook, is stored within it, and then seeing the individual items within that Windows cook, and being able to fetch those items, having them downloaded through your browser and ending up on the file system so you can inspect them as you would normally. Okay, so cooked output, Zen's cooked output store addresses this single line item of writing thousands to millions of files as part of the cook phase. Okay, not huge in and of itself. We've influenced the cook. What about other stages? This is where we start to introduce Zen streaming to target platform. This is experimental in UE 5.5. So what we're doing here is we are looking to minimize copying and transformation, shuffling around bytes into pack, UTOC, UCAS files, and compressing things. That makes sense when we're shipping, but why does it matter when we're iterating? Could we just skip it? In addition, we often don't want to stage to containers at all. So when using the editor quick launch, it builds and launches game. It stages to a non-pack target, which historically has meant just a one-for-one copy of all of the cooked output files from the saved cooked folder to the stage builds folder. How does that work when ZenServer and the cooked output files weren't written, or when we're storing the cooked output in ZenServer and the cooked output files weren't written to the file system? And then finally, we're using Zen over network sockets on the local machine. Could the game executable on another platform, console or mobile device, connect to it remotely? Spoiler alert, the answer is yes. So what does Zen streaming look like? Well, what it means is when we stage to container files, stage to pack files, that process takes everything out of the cooked output out of ZenServer, stores it in the container files, and that allows deploy and run to happen as it did in the past. So that matches the historical patterns. When not staging to container files, we leave the data in ZenServer. We don't copy it anywhere. It's just there. The stage build becomes just the executable and some config. And the game is then expected to connect to ZenServer and get its data over the network instead of attempting to load it off of disk. The end result is that streaming the data from ZenServer greatly reduces the duration of stage and deploy, and it opens up options for faster content iteration. What we're doing here is that we want the data to stay at rest and minimize transformations. So we want to avoid copying the data on the workstation, compressing it, copying it to the target platform. This reduces delay during content iteration and eliminates the need to restage and redeploy as you make and cook changes. All we put on the target device is the executable and a few non-streamable files. As I said, this makes staging and deployment fast. The game on the target platform gets a small file called ue.project_store that tells it identifying information about where to get the actual cooked data from, which machine it's on, port, project identifier, et cetera, et cetera. And then the game on the target is reading the data directly from where it's cooked. We don't have to restage or redeploy. When you've cooked content, it'll be read directly from its cooked destination. And then finally, the other big difference is only the data the game loads, it needs to be streamed over to the target device. This is not like where you're staging, where it's everything that was cooked for your project has to be copied over. It's only what's accessed that gets streamed. So one of the first questions we often get asked is, does this connect and stream fast enough? Like, is this viable to pull all of our game data over the network? So the thing to understand is that the data is streamed over the target platform's retail network, not a dev network, but retail network. And that means we want to make use of a wired connection, which on consoles can be 1 gigabit to 10 gigabit. And on mobile devices, we want this to happen over USB. We do not want this to happen over Wi-Fi. That's not likely to be fast enough or low latency enough for this use case. On Android, we recommend USB 3.2 Gen 2 as a cable and not using Wi-Fi to stream this data. On iOS, we're still evaluating options. The iPhone 15 Pro is the one that came with the higher speed data cable support and is preferred. But again, we're still evaluating things on iOS. At this point, I just want to stress, this is for developers who are making content changes and want to see them quickly on consoles and mobile. This is not for programmers or QA who are trying to test game streaming performance ahead of release. That will always be more appropriately done by installing the full data set over to the target device. And that workflow doesn't go away. It's just now you have a choice to either use that or stream from ZenServer. One implementation detail that's important to be aware of is that for security reasons, ZenServer doesn't accept connections from any other machine. By default, out of the box, it's limited to only accepting connections from the local host. If you want to make use of Zen streaming, then another machine, console or mobile device, needs to be able to connect to it in order to stream that data, and that requires some manual configuration changes as shown here, and that's only appropriate if you are in a trusted or LAN environment. This is not something to do on an untrusted network or public internet. And you can see there what's involved in making those configuration changes in the default engine.ini to allow a remote network service for Zen and to allow Zen to keep running even after the editor has closed by not limiting its process lifetime. Okay, so some context. You're going to see some video here. It looks high speed. What I'm demonstrating is a replay of Fortnite Battle Royale on PS5 at an accelerated replay rate. What I mean by that is not that I've gone and sped up the video after I recorded it. Rather, I did a gameplay replay on the PS5 at an accelerated rate, meaning it ran at this speed on the PS5 originally. My point in doing that was that it demonstrates that even with the additional stress of accelerated playback, we're able to stream data successfully over a network link to have a good in-game experience. The table on the left shows the difference that this workflow has made. So a staged build that is staging to containers produces an 89 gigabyte directory footprint, whereas staging to Zen streaming is only 4.6 gigabytes. This dramatically reduces the time it takes to stage. Again, 18 minutes is shown there, 18 plus minutes is shown there. The time it takes to deploy, nearly 7-minute reduction. However, boot and load takes longer. Fundamentally, that comes down to the fact that streaming from ZenServer is not as fast as reading from local disk. That is a reality. However, that increase in boot and load time is more than offset by the time savings of stage and deploy. So the net result for a person trying to iterate is 25-minute reduction in duration. This is the same example, except from Android using the Lego Fortnite game mode. And again, we see similar behavior where a container build was 30 gigs. However, with Zen streaming, it's only 15 megabytes. There's platform-specific differences about whether the executable ends up in the stage directory or not. So there's a whole bunch of details as to why it ends up exactly that value. But the result is always that you're staging to a much smaller output. And this reduces the time it takes to stage, the time it takes to deploy. But you do pay a penalty in boot and load time. And it's important to be aware of that. However, it's the net result is still 9+ minutes of time savings. We are actively engaging in efforts to see what we can do to reduce the boot and load time impact by doing things like caching on target platform, as well as looking for bottlenecks in our the loading code that makes use of Zen streaming. However, to a user, this is faster turnaround time, and the in-game experience is indistinguishable from if they had it installed on their local device. I should mention as well, I've put these graphs on this screen. They illustrate the throughput in bytes as well as the number of requests happening to ZenServer second by second. Okay, so choosing to make use of Zen streaming on target platform has addressed a whole bunch of our challenges in the stage and deploy phases of our pipeline. So that's great. I think at this point it's good to just stop and think back to where we started and where we're at. This was the diagram, the illustration of where we started. Again, make note of your stage build was 65 gigs spread over 80 files, and that same build had to be deployed over to the target device. Now, when we're using Zen streaming and the aforementioned features, our DDC data is in ZenServer, our cooked output data is in ZenServer. It's high granularity, it's still 1 million items. However, that's not 1 million files on the file system because ZenServer is choosing how that's represented, and it's much more aggregated. And crucially, because we're streaming, the size of our staged game has gone down to only 5 gigabytes over 50 files, and that's all that needs to be deployed to the target platform. And then once you launch your game, it is able to connect to ZenServer and stream the data that it needs from there. Okay, so stage and deploy are in good shape, but we want to do more to reduce the cook phase. This is where we start to introduce a couple more features. Specifically, we'll start with Zen Snapshots. This is something that's experimental in UE 5.5, and the premise behind this is that we don't want to cook when we don't need to. So if a cook has been produced elsewhere by another person or on the build farm, you should be able to get it efficiently. And getting a cook should be equivalent to cooking for yourself. So there are existing mechanisms for getting staged container builds or fully project game images, but that's not the same as you having cooked the data yourself. They represent later or different states in the data pipeline. So what is the equivalent of what we could do in the past? That is copying a cooked output folder. But what's the equivalent of that when we're storing our data in Zen? Well, when ZenServer holds the cooked output state, can we relocate that from one machine to another? And is there anything outside of ZenServer that's an expected part of the cooked data? So this is where snapshots come in. They represent the ability to export and import cooked output state for one or more platforms from ZenServer and store them in either Unreal Cloud DDC server, another ZenServer instance, or as a file archive. This is done efficiently by getting and transferring only a delta of what doesn't already exist in the destination. So we're still building up the tooling around this, but in 5.5, you do have access to a UAT task called Zen Export Snapshot, and the build and test project XML build graph that ships with the engine demonstrates the use of Zen Export Snapshot and provides an example of how to export snapshots to Unreal Cloud DDC from your own build jobs. One thing to be aware of, exporting a snapshot writes a small snapshot descriptor file, and that file is just a few lines of JSON that describe where the snapshot data is stored. And this becomes important when you're now trying to import a snapshot. As before, we're still building up this tooling, but in 5.5, we provided access to a ushell command, .zen import snapshot. You can pass as an argument to that the snapshot descriptor path, and it will import the described snapshot into your local Zen server. And at that point, you are in the equivalent state as the machine that did the cook that snapshot was exported from in the first place. It's also important to be aware that snapshot data stored in Unreal Cloud DDC can be replicated between regions. So what this can look like is you might have a build farm in a particular regional location. So let's say your build farm is in US East, hosted in US East. And you have builds that are publishing snapshots at some cadence from the build farm. And they publish to the US East Unreal Cloud DDC server. A user in another regional location can be talking to the Unreal Cloud DDC server in their region. In this example, a user in Europe could be talking to the Europe Unreal Cloud DDC server, request that snapshot. Behind the scenes, the Europe Unreal Cloud DDC server is fetching whatever it doesn't already have from the US East server and sending the result back to the user who requested it. This data is replicated and cached so that the next user who asks for it will find that everything is served to them immediately from the Europe server without having to go fetch anything from the US East server. And all of this is done in an incremental manner. So only the difference of what they don't already have has to be downloaded. Conceptually, snapshots encompass the entirety of the cooked output for a target platform. They don't contain the executables for that target platform, so you need to build or get those separately. And once you have imported a snapshot, you are able to do everything you could do if you had cooked that data yourself, meaning you can stage to a Zen streaming build, then deploy and run that. You can stage to a container build, pack files, deploy and run that. And crucially, you should be able to cook incrementally on top of it. And this leads to the last subject that I wanted to discuss, which is incremental cook. This is a future work item that we're working towards for UE 5.6 and beyond. And fundamentally what this is about is we only want to cook what needs to be cooked. This has been a long time goal. Iterative cook has existed for a long time, but it didn't recognize all types of dependencies that exist within our data. What we want to get to, our target workflow, is you get a base cook and build only your changes on top of it. For us, that's the optimal arrangement and brings duration of target iteration into the range that's acceptable for more people. And the way we're approaching this work is we're trying to take a reliability first approach. And that means excluding types that we know have dependency tracking issues, even if it means assets containing those types have to cook fully each time. That's how we're breaking down this problem into pieces. So, one of the important questions we had to ask ourselves as we started to go about this work is, how do we know that incremental cook is producing correct results? Are we just hoping and then we'll wait for somebody to report an issue to us? That's not really what we were after. So what we're doing is we've got automated jobs that cook incrementally at head revision of our internal projects, Fortnite and others, and compare the output with that of a full cook. This is a byte for byte comparison. And when there are differences, they can be due to non-determinism, or they could be due to a gap in dependency coverage of our incremental cook. And we've been using that to get a better understanding of where those gaps are and following up on them and getting them addressed. So our goal is to be confident that it's suitable for developer iteration. I want to be clear that it is separate to get to a point where it's suitable for shipping builds. That's not what we want to use incremental cook for at this point. What we want is for it to be suitable for developer iteration. Internally, there's a lot going on to track dependencies to try and make this reliable. Sometimes people think, oh, well, packages declare their imports. Those are the dependencies, right? No, not exactly. There's many more types of dependencies, and even the imports aren't necessarily all cook dependencies. So for example, you can have dependencies on non-asset files. For example, a shader, USF or USH file. You can have assets on another package. You can have dependencies on a CVAR value. You can have dependencies on an INI config, as well as class schema, meaning the description of the fields in your types. If those change, the cooked data needs to know that it needs to rebuild. So that has to be represented as a dependency. And really what we're after is addressing these last three big issues with the cook phase through the use of incremental cook. There'll be more to come on this subject in the future. Okay, wrapping up. We set out to do improve content iteration speed on consoles and mobile, enable content iteration on target platforms, be closer in speed to code iteration on target platforms. I'm not here to say mission accomplished. However, we've set out a path that allows us to get to that destination, and we're continuing to work through that path. The thing to be aware of is there's a number of separate distinct things that are helping with this, each of them completing on a different timeline, whether it's stuff that was production ready in 5.4, stuff that is production ready in 5.5, beta in 5.5, or the items that are experimental and are going to be completing in the future. So I promised documentation. The situation I want to avoid is one where people hear about this stuff, but then get back to their desk and don't know how to make use of this stuff. So for that reason, I've put up some documents that are step-by-step how-to documents for how to set up Zen as a shared DDC, how to use it as cooked output store, how to make use of Zen streaming, and how to make use of cooked data snapshots. And that's it.